So how does this help prove that the pictures that we're getting from NASA, from the International Space Stations, are fake? Because and if from 300 miles away from me, something appears as a dot, then should I still be able to see it from here? The data, it doesn't resolve it, and so then just it's a blurry, and then just you can't see it at all. The radius of the Earth is 3,959 miles. The diameter
of the Earth along the equator is 7,926 miles, and from pole to pole is 7,900 miles, because the Earth is an oblate spheroid, and so it's fatter in the middle and it's pear-shaped, and so the slightly different, slightly shorter from pole to pole than from side to side along the equator, along the middle.
Looking at the globe Earth model, if you're flying at 33,000 feet, then that's 7 miles and above the globe. And so you're really at a distance of about 0.17% above the Earth, relative to the circumference of the Earth. No, relative to the diameter of the Earth. So if you're flying 7 miles above a sphere with a diameter of roughly 7,913 miles as an average, then you would be the height, the distance between the surface of the Earth and your plane relative to the size of the Earth would be 0.009% of the circumference of the Earth. That's how much of a distance above the Earth you would be. From that distance, one wouldn't expect to be able to see any curve because of your visual vanishing point. Also, when you're that high above in a plane looking down, you'll notice that if you fly over the Rocky Mountains, the depth of field is shortened so that you see the top of the mountains and you see the bottom of the valley floor, and the distance between those is collapsed, shortened, and so it looks like a model that you'd see on a desk where this a couple centimeters difference between the top of the mountain and the valley below. And so if you're looking to the horizon, then any height differences would also appear foreshortened. When you combine that depth of field collapsing so that differences in height are less noticeable, are less pronounced, and the tiny circle of the actual planet beneath you that you're able to see, these things come together so that when you're in a plane, you wouldn't be able to see any of curvature of the Earth. If you do think that you're seeing curved Earth of the spherical globe, that's one of two things. It's either the windows on the plane, just they're either rounded to fit the round side of the plane, and so that creates a distortion, and then you end up seeing straight lines a little bit curved, or your expectation is shaping your perception. And this is a well-established phenomena where a lot of times we think we see what is actually real in there. That's not the case. What we see is filter through what we expect to see, what we understand about the context of what we're seeing. And so if you expect to see the curve, then you might be seeing some carving, but it's just an illusion. And actually, if you were to hold a ruler up to the window, you would see that there's no actual curve. Just something to keep in mind. Having said that, I've seen a lot of videos put out by flat earthers that are trying to prove the flat earth by saying, since we see that the horizon is a straight line, then the earth must therefore necessarily be flat. That is not quite correct because of how our vision works. So the lens of our eye, and we have this pupil in the middle is this big hole, and the optic nerve enters the back of your eyeball, and this big gap in the middle of your vision that your brain has to fill in the information for to make a full picture. And like I mentioned before, expectation shapes perception, context shapes perception. The brain is filling in all the information from what it can't get in the middle of your field of vision, from context cues, prior experience. So we have to be really careful about assuming that what we see is actually what is. One of the things that is relevant about how our eye sees has to do with the angle of light entering into the lens of our eye and how that affects what we see at a distance. So if an object is very close to your eye, then the light from above is just down here, it's this angle, and then the light from beneath is just up here, and then just this little angle, and then your eye flips it, oh no, and then your brain flips it and makes the proper image, and then this is what you see, and everything that's in the line with your pupil, your brain just makes it up based on the information around it. This is why if you're looking at the Pleiades constellation, you can actually see it more clearly if you look a little bit to the side of it. If you look directly on, it's a bit harder to see, and our eyes are actually shifting when we see the saccades anyway. So when you think you're looking directly at something, your eyes are actually making little micro movements. And so your pupil is never really going to be in the same place or pointing at the same thing all the time, even if you're looking directly at something. And so that's part of how the brain gets information about what's in that gap. But so if you look at the Pleiades constellation dead on, then although your eyes are moving around a little bit, so your brain gets enough information to give a fuzzy image, you'll find that if you look a little bit off to the side of the constellation, you suddenly see it more clearly. So you actually end up with more information, more visual information, and a better sight of it, even though you're actually looking at it in your peripheral vision. As objects move further away from you, then the light from above and the light from below the object is actually closer and closer together. What happens in the middle? In the middle, there's no information coming from the middle. That's the information that your brain has to make up from context and expectation. So if you're looking out at the ocean on a blue sky day, you will see the sky meet the water at that false horizon line. But what's actually happening is the light from above and the light from below are kind of being smushed together into one picture. If you see a boat floating away towards the horizon on the ocean, then as it moves further and further away, you'll notice that it moves further and further up. But what does it do at the horizon when the ship disappears? So in the past, actually up until, well, for some of you up until this moment, we believed that the ship would go over the curvature of the Earth and disappear. And this is why the bottom of the boat would disappear first, and the sails were the last things to disappear, to sink beneath the horizon line. But now we know, and especially through the use of these super zoom lenses on new cameras, the Nikon P900, P900X, P90X, I think that's an exercise program for people who have to go to jail. You look at the horizon, you see the ship disappear over the curvature of the Earth, and then you take your camera and you zoom in, and all of a sudden the boat is still there. The boat has not disappeared over the curvature of the Earth. It's clearly visible in your camera, just happily floating on the ocean. So why does this happen? This happens because we have a certain vanishing point to our perspective, beyond which we just don't see, we can't resolve anything beyond that point. So the angle of the light coming in from that distance becomes parallel, and then because it's at the center of your eye where your pupil is and your optical nerve, then this into the back of your eyeball, you're not actually, you have no way of getting information about that point. And so your brain just fills it in. So how does it fill it in? Well, it takes what's at the top right above that, and it takes what's at the point right beneath that, because basically it takes what the first row, let's say, of rods and cones above the hole in the back of your eye, and then it takes the information from, let's say, the row of rods and cones that are right beneath the hole in your eye, and then it just patches in the same thing. And then it takes context cues, so it looks at what's happening on either side, and it just kind of fills it in, like a Photoshop Band-Aid tool where you can heal an image with the Band-Aid tool in Photoshop, and it just takes information about the surrounding area and then just makes an educated guess based on the pixels and stuff. And what happens then is that's your vanishing point, when the light becomes parallel to the center of your eye, and then there's no information reaching your brain for what's happening there. And so effectively the boat vanishes. Why does the bottom of the boat vanish first? Because the sail of the boat is actually higher than the horizon, the midpoint of your eye. And why does the horizon always rise to meet eye level? Again, this has to do with how the light interacts with the lens of your eye and the round shape of your eye and all these things that just happen, so that the horizon is always going to be eye level because your eye is taking the light from up here and the light from down here around the hole in the middle of the eye and smushing it together in the middle, and then that becomes that horizon. But what does this mean for our ability to see things that are very far away? Well, we don't see things well that are very far away. Especially not if they're small enough that at that distance they'll end up in the middle of our blind spot, and then the brain doesn't have any information around it to fill that in. If you have Waldo in the middle of your blind spot, then there's no Waldo around Waldo, and so your brain can look at all of what it can see, not Waldo, and try to fill in the blind spot, Waldo. But because it doesn't have Waldo around it, it's not going to fill it with Waldo. It will just fill it with more non-Waldo. Our eyes are constantly moving a little bit left to right, the saccades, but not so much from up and down. The context cues that the brain can use to build the image, it can use more information from the sides than it can from directly above and directly below. Yes. So how does this help prove that the pictures that we're getting from NASA, from the International Space Stations, are fake? Because is when you look at the pictures from the International Space Station, you can see the stars, little points of light in the sky sometimes. Sometimes you see no stars. And people have brought that up as, why can you not see stars? You should be able to see stars. The aperture of the camera, when it's supposedly taking a picture of the Earth, would have to be such in order to get that level of detail. The aperture would have to be actually quite small in order to get the amount of detail. And so you would expect to get just little starlights. There are some pictures from the International Space Station that show stars in the background, and you see them as these little points of light. Here, when you look up at the sky, you see stars, little points of light. That's a problem. Because the International Space Station is about 240 miles above the surface of the Earth, according to NASA. If the International Space Station truly is 240 miles above our heads, and it's taking pictures of stars as just little dots of light in the sky, and we're 240 miles below, then we shouldn't be able to see stars at all. In the same way that I can show you a period, or a freckle maybe. In the same way, I can show you a freckle, a little freckle, and you can see my freckle from here. This is a little dot of brown on just pale skin. And if I move further and further away from you, there's a point at which you will not be able to see the freckle. You will see my arm, it's this pale surface, but you won't actually be able to see the freckle. Your eye doesn't have the resolution skills. Just can't. It's just all trying to make up the light bouncing all the information. And so if I were 240 miles away from you, you also could not see the freckle. In fact, you could not see me standing there. Even if I were on and then all the hours passed while I waited for my card to download to my computer and my battery to load, multiple batteries to charge. And now I have no idea where I was. Something about a freckle. Some people have tried to say that because the stars are emitting photons, this is why we can still see them, but there's a problem with that theory that people just sometimes claim as truth. And the problem with that theory is, well, there are two. So people often give the analogy, in the same way that you can see a laser pointer from really far away, you can still see starlight because the photons are just rushing towards you through the vacuum of space, through the atmosphere, all this light scattering atmospheric effects. This is why stars sparkle. And then into your eye. But a laser beam, the reason that you can see laser light from a far distance is because of what lasers are. And this is why lasers are different from flashlights. Because laser light is coherent light. And so all the photons are just all coherent, all sharing the same phase. They're all kind of moving together. And so then because they're all moving together in this one unified wave, rather than having different polarization directions and maybe slightly different amplitudes because of the different frequencies of light, because they're all the same, then they are less scattered. Laser light is very different from starlight because starlight, it's being emitted according to the model that science, the common sense, the model that we're taught. Starlight is going to be emitted at different frequencies, at different spectrum of light, and it's going to go through galactic dust and all kinds of obstacles and just gravitational lensing around galaxies, all kinds of things between the star and your eye. We're taught that sunlight, when it hits our atmosphere, it is deflected and in so many ways scattered light, and so that's why we see the sky as blue, because blue light is the most easily scattered. And so when the light is just scattered all around by all the little molecules, these atoms in our atmosphere, ozone and oxygen and nitrogen and carbon dioxide, and then all the dust and all the pollution and the water vapor. And so when our sunlight goes through all of that, it gets all scattered, and so the effect is this blue sky. And then we see the sun as more yellow, orangey, red, because the closer to red you get, the less easily scattered that light is. And then it's all of the science is just breaking down all around us. This is probably why Neil deGrasse Tyson is throwing microphones on the ground and smashing all the things. Just all lost. If from 247 miles away you see it as a dot of light, then you shouldn't be able to see it from here. If from the International Space Station stars were, I don't know, saucer sizes, dinner plate sized, bigger, and then from here, then we would see them as points of light in the sky. Then that would make more sense. Kind of, but not really. But kind of. But the fact that they're seen as just little dots from the ISS, it suggests that that we shouldn't see them. How far away can the human eye see? Well, we can't see the boat past the vanishing point of our vision. And so when we take our zoom lens and we zoom in, the boat reappears. Therefore, it's still in our line of sight, but it's beyond our vanishing point. That suggests that our vanishing point is not that far. So if the vanishing point, the false horizon, is not that far when I'm looking straight ahead of me, then when I look up, shouldn't my vanishing point be at the same distance? So if a very large ship sailing away towards the sunset disappears at a certain point, then shouldn't a boat-sized object above me then also disappear at that same distance? And if from 300 miles away from me something appears as a dot, then should I still be able to see it from here? We can't see the International Space Station with the naked eye. This is too far, this itty bitty. You cannot resolve it. People are using their zoom lenses of 83 times magnification to take pictures of what appears to be this fuzzy hologram. The point being that when you ask, if you ask just general common sense-ish community, how far can the eye see? There aren't a lot of good answers. People will say, we can see billions of years, because when we look up at the night sky and we see these stars and they're billions of light years away. Therefore, we can see billions of light years. And that worked as that may have worked as an explanation to give people when you were telling them that the boat is no longer visible at the horizon line because it's gone beyond the curvature of the Earth. But now when we have the technology to demonstrate for ourselves that the boat has not gone over the curve of the Earth, that the boat is clearly in our line of sight, we just have a vanishing point beyond which we can't see, then it becomes nonsensical to say that our vision is limitless. Are stars like lasers? Demonstrably not. By the very fact that the sky is blue and we see the sun as yellowy orange, that clearly demonstrates that stars don't put out light like a laser beam, that it's not all at one frequency, just wave. You get white light from the sun, you pass it through the prism, and then you can see all the different rainbow colors, because that white light, that sunlight, has the various light frequencies that make it up. So it's obviously not in any way like laser light. Stars are not lasers. Also, our atmosphere is full of things, obstacles. For starlight to go through the atmosphere, through that scattering effect, and still present this little point of light that looks identical to the points of light that we see in the ISS videos, that it doesn't make sense. It just doesn't seem to make sense. So if you can help me in a kind and respectful manner figure out how we can establish where our vanishing point is and how far we actually can see and why we can see the stars above but not the ship in front of us, then please leave a comment below and we can have a little conversation in the comment section if it's respectful and friendly and helpful and not just nonsense science says that isn't actually supported by strong logic or proof, critical thinking skills. If you like this video, please consider sharing and subscribing, maybe giving it a thumbs up, just for liking. I don't know why. We shouldn't be discouraged from asking these questions. We should be encouraged to try to think about the world that we live in and to try to think about the science that we're taught and reevaluate. Does this work with new findings? Does this work with new understandings and new contexts and perspectives? And so, what's the meaning of the flat Earth?